observation of Einstein's theory of general relativity. At the center of almost every galaxy lies a supermassive black hole, which could be from hundreds of thousands to billions of times the mass of our Sun. They are thought to be the glue that holds galaxies together. Now, the first hints that stars orbiting around one of these supermassive black holes are affected by Einstein's theory of general relativity have been published. A group of physicists studied the movement of a group of stars around the black hole at the center of our own galaxy, called Sagittarius A, which is about 300,000 light-years away. The team found suggestions of a small change in the motion of one of the stars, known as S2, in line with the predictions of general relativity, which Einstein published over 100 years ago. The paper has been published in the Astrophysical Journal. This result is an echo of nearly a century ago, when the mysterious precession of Mercury's closest approach to the Sun happened in contradiction to the predictions of Newtonian gravity and mechanics, said Jamie Matthews, professor of astronomy at the University of British Columbia, who was not involved in the study. At the time, Einstein's theory of general resolved the mystery, making the results one of the first of many successful tests of the theory. Now, almost 100 years later, the theory seems to have passed another test, regarding tiny fluctuations in the movement of stars in the center of our galaxy, which is an incredibly difficult thing to detect. The center of our Milky Way galaxy, about 30,000 light-years distant away, was observed through 30,000 light-years of interstellar smog, gas and dust dispersed amongst the stars, said Matthews. These are extremely challenging measurements to make and to model. These are tiny deviations that require high-precision techniques and a very careful analysis of data, which have not been done so far, said Vladimir Karas, from the Czech Academy of Sciences and one of the study's authors. Although we did expect that our results would eventually reach agreement with the predictions of general relativity, I am very happy that we see the effect at work. Some of the community is wary of the results, commenting the findings are not statistically significant enough to be called a discovery. It's an interesting start of a development of a new technique, but is very premature, added Professor Andrea Ghez, head of the Galactic Center Research Group at UCLA. A research group at UCLA is working on similar observations. Ghez explained the confidence level of the result was only given to 1 sigma, when in science a confidence of 3 or 5 sigma is usually needed to be called a discovery. 5 sigma corresponds to a probability value of about 1 in 3.5 million that if the effect were not there, the team would have seen the results presented. However, Andreas Sickart, lead author of the paper, says he is confident in the methods used. We consider this as a clear hint at relativistic effects taking place as expected in the high mass limit of 4 million solar masses as derived for the central black hole, he said. The estimate of the relativistic parameter in this paper is consistent with 0, within a single error bar, so one must take this with a grain of salt, or an interstellar dust grain, Matthews said. But a 1 sigma result about space-time near a supermassive black hole is better than any we've had to date. As usual, all of this can be done with a higher precision in future, but currently with the existing data this is the very best that can be done, Sickart argued. Other research groups, including one led by Ghez, will be making more observations and hope to release more precise results next year.